In this video, we'll discuss a simple but powerful theory for describing reaction rates. Transition state theory. The main idea of transition state theory is that reactants form an equilibrium with a transition state or activated complex. So as an example, we can write a reaction of a diatomic molecule AB, which equilibrates with our transition state, which we'll call AB double dagger, and then decomposes irreversibly into a product, A plus B. So we'll call this P. So we can write rate equations that look quite similar to ones we've developed before, so with reaction rate constants K1, K minus 1, and K2. But note here that while this looks similar to one of our previous series of elementary steps, here AB double dagger is a transition state rather than a stable intermediate. So on a reaction coordinate diagram, this might look something like this, where we have our reactant AB, our transition state AB double dagger, and then our dissociated products A plus B. So here the reaction coordinate might be the stretching vibration along that bond between A and B. So we can write our rate in this case as the change in concentration of our product with time. And so that's going to be equal to the reaction rate constant K2 times the concentration of this activated complex or transition state AB double dagger. So assuming a pseudo steady state approximation on AB double dagger, we can write that the change in concentration of this species with time is going to be essentially equal to 0. And so this is going to be equal to K1 times the concentration of AB minus the sum of the rate constants of the two reactions which consume our transition state AB double dagger. So that'll be the first reaction in the reverse direction and the second reaction in the forward direction. So solving for the concentration of our transition state AB double dagger, this comes out to K1 divided by the sum of K minus 1 plus K2 times the concentration of our reactant AB. So we can write the rate of formation of our product as K2, the reaction rate constant for step 2, times K1 over K minus 1 plus K2 times the concentration of our reactant. So that's simply K2 times the concentration of our transition state. So again, in transition state theory, we're going to assume that the reactants are essentially equilibrated with the transition state. So what that means in terms of the reaction rate constants is that K minus 1 is much greater than K2. If this is the case, our reaction rate equation is going to simplify a bit. So our denominator here is just going to be equal to K minus 1. So our overall rate expression will simplify to this. And you should identify that this term here, K1 over K minus 1, is an equilibrium constant for the first step. And so again, that's the equilibrium between our reactants and our transition state. So we can write the equilibrium constant as the concentration of products, which in this case is our transition state, divided by the concentration of reactants. But we have no real way of evaluating the concentration of our transition state. However, we've also seen in a previous video that we can write the equilibrium constant in terms of partition functions. So that's going to be equal to the overall partition function for our transition state divided by the total partition function for our reactant. So these partition functions are multiplied by a term e to the minus delta E over KT, where delta E is the difference in the ground state energies between our reactants and products, or in this case, the transition state and the reactant. So this difference in ground state energies between our reactant and transition state is simply equal to the activation energy for the reaction. So that's equal to this distance here, the ground state energy between reactants and the transition state AB double dagger. So plugging this into our rate equation, we can write that the overall rate is equal to the rate constant K2 times the total partition function for our transition state divided by the total partition function for our reactant state times e to the minus activation energy over KT times the concentration of our reactant AB. So if we group all these terms together, we can see that this is our reaction rate constant K. So for this elementary reaction, the rate is equal to a rate constant K times the concentration of our reactant. So if we know our partition functions, we can evaluate the magnitude of this rate constant. So this gives us a powerful theory for understanding and predicting rates. So let's keep looking at this expression for our rate constant K. to get to a more useful form. So the rate constant K2 here describes the rate of decomposition of our transition state, AB double dagger, into product, in this case, A plus B. So here, since our reaction is dissociation of a diatomic molecule AB, the reaction coordinate, again, is the stretching vibration between A and B, and activation of this vibration weakens the bond between A and B. So we can see this pictorially. So we have the stretching vibration between A and B. So eventually, if we stretch the bond any further than it is in the transition state, so this is our AB double dagger, it will decompose into our product A plus B. So the rate at which the transition state attempts to do this is equal to the frequency of this vibration, which we can just denote nu. So then our rate becomes equal to the frequency of the vibration between A and B times the total partition function of our transition state over that of our reactant state times e to the minus activation energy over kT times the concentration of AB. So here we can express the total partition functions as a product of the partition functions associated with translational, vibrational, and rotational modes. And so here we'll assume that the electronic contribution to the partition function is negligible. Because of this, we can express the total partition function as the vibrational partition function along the reaction coordinate times all the other mode. So we'll rewrite our total partition function for our transition state as equal to just the vibrational component along the reaction coordinate, so that's just one vibrational mode, times everything else. So we'll denote this with a tick, and so this will be the translational, other vibrational modes, and rotational modes for our transition state. So as we've seen in a previous video, we can write the partition function for a vibrational mode as 1 over 1 minus e to the minus h nu over kt for that vibrational mode. So this is the frequency of that vibration. And since at the transition state this vibration is one of a partially broken or weakened bond, its vibrational frequency is going to be very low. So mathematically, if we have a small value of nu, our frequency, we can approximate this term 1 over 1 minus e to the minus h nu over kt as being approximately equal to kt over h nu. If we plug this into our expression above, so here I'll just write the reaction rate constant, so that's going to be the frequency of vibration along the reaction coordinate times the partition function for the transition state associated with vibration along the reaction coordinate, which is kt over h nu, times the total partition function for the transition state with that one mode removed, divided by the total partition function for our reactant AB. And this is all multiplied by e to the minus ea over kt. So here, this frequency is going to cancel, and we can arrive at a final expression for our reaction rate constant. So it's equal to the Boltzmann constant kBt over Planck's constant h times the total partition function for our transition state with one vibrational mode removed divided by the total partition function for our reactant AB. And this is all multiplied by e to the minus ea over Boltzmann constant times temperature. So here transition state theory has given us a physical justification for the Arrhenius type rate expression for an elementary reaction. So we've been writing that rates are equal to a reaction rate constant times the concentration of our reactant for an elementary step. And we can further write the reaction rate constant as some pre-exponential factor A times e to the minus ea over RT. And so this gives us a physical justification for where this comes from and has given us some guidance as to what the pre-exponential factor A is. So here we can see that this term kt over h times the partition function of the transition state divided by that of the reactant state is our pre-exponential factor A. In subsequent videos, we'll see what the thermodynamic interpretation of transition state theory is, and we'll see some examples of how the pre-exponential factor can be calculated using transition state theory.